Very happy you made it here, and also welcome to all the people on Zoom. It's my great pleasure to introduce today's speaker, Professor Nicolas Pavloff, who is professor at the Université Paris-Saclay in France. So it's a long distance, and we are very happy that he can make it here, even though it's this late evening by now. So Nick actually started out his career with a PhD on inhomogeneous systems of liquid helium. So he developed a density functional theory that was able to describe situations where liquid helium is strongly perturbed over very small distances. Then from 1990 to 1991, he went as a postdoc to the Niels Bohr Institute in Copenhagen, and there he started working on metallic clusters. And in 1991, he went to Paris Sud Université as a maître de conférence. And he started working on semi-classical description of diffraction in quantum billiard. This is probably something where he has some overlap with you as well.
Exactly.
Then in 1999, he got his French habilitation, which is the ability to be a professor, on titled Physics of Metallic Clusters and Semi-Classical Expansions. And then since 2014, he's a professor at the Université Paris-Saclay. And his research interests are actually fairly broad and are very, very modern topics. And a lot of us have actually interest in many of these fields too. They include, for example, the theory of quantum fluids and nonlinear phenomena in quantum systems, including transport phenomena, superfluidity, disorder, quantum turbulence, quantum defects, solitons, dispersive shock waves, and analogs of Hawking radiation. He has written a number of very nice publications on various topics, for example, topological pathways to two-dimensional quantum turbulence, which is also the title of his talk here, violations of Bell inequalities in an analog black hole, oscillating solitons and AC-Josephson effects in ferromagnetic BECs, bipartite and tripartite entanglement in Bose-Einstein acoustic black holes, shockwave dynamics in the fluid of light and more. So it's very interesting topics, and we are very excited that he can be here today, at least through Zoom, and tell us about his work. Nick, please.
Thank you, Peter, for this nice, very nice introduction. So let me start sharing my screen, if it seems to work. Yeah. So I'm very happy that you give me this opportunity to present your results, as I said, which are well known in some community, but not well known in condensed matter, and which rely on the use of concepts which have a wide range of applicability, from the study of the tide, as shown in the left plot, down to the study of turbulent polariton superfluid. I will present what these objects are. And as you can see, the typical length scales are quite different. And also the time scales. The time scale in the polariton physics is of order of picoseconds. And of course, for the tides, it's of the order of a few hours. So all that is about turbulence, and at least in 3D, yeah, concerning turbulence, we have in mind that in 3D, there is this so-called Richardson cascade, that big eddies decay into smaller ones, and so on and so forth, until one reaches the viscous scale. And at this scale, energy is dissipated. So that's Kolmogorov cascade in 3D. And actually, in 2D, there is a similar cascade, but it's inverse. The wheels, the eddies, tend to gather together and bunch into larger eddies. And for instance, it has been observed in several experiments. This is one of a possible experiment. I will discuss this one. It's a nice tabletop setup. You just it's a soap film between the two threads here. The soap it goes down, the film goes down due to gravity. And here you see at C, there is a grid where wheels are created. And when they go down, they increase in size. So this is called the inverse cascade. And it has been observed in many classical settings. And it's believed also to be at least partially relevant, say, in the atmosphere of Jupiter. So the great red spot is such an eddy. So maybe it's a bit more complex because you have several layers in the atmosphere, but at least there is this tendency to gather. For instance, in 39, 3 white ovals were created, which recently merged 5 years ago to form a red spot junior. So there is this tendency of vortices, eddies, together into large structure in 2D. And in order to explain this phenomenon, Onsager in 49 used an old model due to Kirchhoff. It's a 2-dimensional model where vortices are point-like. So it's a bit of a mathematical model, but still it has some relevance, as I will discuss later on. So you consider n vortices in a 2-dimensional, incompressible, and frictionless fluid. So it's 2D. The curl of the velocity is along the z direction. The velocity itself in xy. And you assume that the vorticity omega is located on a series of points Ri. Ri is called a point vortex. And the model goes on that goes this way, that each vortex is dragged by the velocity field created by the n-1 others. Okay, each vortex has no inertia. It just follows the velocity dictated by the field created by the others. And this model can be cast under Hamiltonian framework. You can write a Hamiltonian. And the equations are easily derived, and you find that actually x and y are canonical conjugate variables. You see the equations x dot I for vortex I is dh dy, and instead y dot is minus dh dx. And then Onsager just made the remark that for such a system, the phase space has a finite volume. Indeed, it's just the surface of the system A to the power n, where n is the number of vortices. And in all these type of systems, the entropy saturates, and one reaches configuration with negative temperature. It's easily shown. I will not lose time to show it, but it's really, I mean, the same situation occurs, for instance, in a Ising system, in a finite Ising system. And so you have regions where entropy increases as a function of energy. Energy is the horizontal axis, and then decreases. So we are used to the fact that configurations of high energy are allowed at positive temperature, provided they correspond to an increase of entropy, because one minimizes E minus Ts. But when T becomes negative, T is T minus 1 is dsd here. When T becomes negative in this gray region there, high energy configurations are allowed, provided they have small entropy. And in this case, to decrease the entropy, it so happens that the vortices bunch together in clusters, schematically represented here in blue and green, clusters of the same vorticity. The blue vortices, say, have a vorticity plus, and the green ones have vorticity minus. And in the saying of Onsager, if T is negative, vortices of the same sign tend to cluster so as to use up excess energy at the least possible cost in terms of degrees of freedom. It's just another way to say that you need a small entropy. And in this paper, Onsager acknowledges that, I mean, this is a model that has little connection with real classical vortices observed, say, in the subfilms I was discussing before. But in a footnote, he says that maybe it's important for superfluids. And indeed it is. And point vortices have been observed in superfluids. I will discuss what is the reason for that. And clustering has been observed, and I'm just presenting some experimental results. So the upper plots correspond to a two-dimensional Bose-Einstein condensates of rubidium atoms. So it's a bosonic superfluid. And indeed, these are experimental results of a group in Australia. Indeed, a type of clustering has been observed. It's not very convincing, but you see here the blue vortices have the same vorticity. They turn in the positive. The velocity is oriented in the positive direction. Instead, for the green ones, the velocity is no, for the green, yeah, it's negative, and for the blue, it's negative and green positive. Sorry. And things have been observed more convincingly in a polariton system. This is the figure below here. Indeed, it's not so clear as the schematic illustration I presented earlier, as this one, but there you may say that indeed clusters of the same signs, say blue, tend to bunch together, in vortices, sorry, of the same sign, tend to bunch together into clusters. And the same for the red-colored vortices, which have an opposite vorticity. So maybe I should present what are polaritons rapidly, because they are not so familiar objects. These are quasi-particles. It's hybrid light matter. So what you do schematically, you take two very good mirrors here, the blue and green ones, and in between you put a semiconductor. And in the semiconductor, you may excite something which is called an exciton, which is already a quasi-particle. It's a particle-Hall bound state. And then in some configurations, this bound state is resonant with a mode of the, say, Fabry-Perot cavity between the two mirrors. So what happens is that you create an exciton, it decays, emits a photon. This photon is resonant in the Fabry-Perot. It excites again an exciton, and so on and so forth. And you end up with a quasi-particle which is half matter, half light. And these objects have been, these are bosons, and they experience a strange type, but still a type of a Bose-Einstein condensation. And this is how the objects I will discuss in the second part of the talk. So, but then the question is, why is it that point vortices are observed in superfluids? And the reason is simple, actually. It's connected to the order parameter describing a superfluid. The order parameter is typically a real scalar, non-real, scalar complex, a function with an amplitude and a phase. And say, for instance, if you consider a ground state, which is stationary and uniform, the amplitude is constant, and the phase has a trivial time dependence, where you can show that this object here, mu0, is the chemical potential. Now, if you make a Galilean boost at a velocity v0, the phase is modified, mu is changed, but the important thing for us here that you get this part here, this mv0 dot r, mv0 being the momentum. And this generalizes to a non-uniform velocity. And in this, for such a system, you may show that the velocity field is actually the gradient of the phase. It's a local function, and up to a factor h bar divided by m, it's the gradient of the phase. There are several ways to justify this behavior. This is just one of them, but it's a well-known, I mean, it's very useful results of superfluid physics. But then, since the velocity is a gradient, this imposes that its curl is 0. The flow is irrotational, so bad news for vortices, except if there are points, let's denote them as Ri, where the phase is ill-defined. And this occurs when the amplitude is 0. Of course, if the amplitude is 0, the phase is defined. And then you may have a vorticity, omega, remember the curl of V, which is a series of delta located on this point where the amplitude is 0. So indeed, this is the only way to produce vortices in a 2D superfluid. Okay, and on top of that, Onsager briefly commented on that, and Feynman wrote the result more carefully, showed that the vorticity around such a vortex, the circulation of the velocity is quantized. So consider one of these vortices and compute the circulation of the velocity field around Ri. So this is this object here. Of course, by Stokes' theorem, it's gamma I, this prefactor here. But since V is a gradient, it's also the change of phase around the contour up to a factor h bar divided by m. So, and it's h bar divided by m, 2 pi n, because of course the phase should change by a factor 2 pi or an integer multiple of 2 pi during a round trip. Otherwise, the order parameter will be multiply valid. No, will not be uniquely defined. So this ni should be an integer, and typically it's plus or minus 1. It's if you have a vortex with, say, ni equals 2, it decays into 2 smaller vortices. So indeed, for superfluids, you expect that vortices are point-like, and on top of that, the vorticity should be quantized. But actually, this is not the result which is uniquely valid for superfluids. And the first quantum vortex, so to say, quantized vortex or point vortex, was observed by an individual. I don't know how to pronounce it. I think it's Ewell, but I'm not sure. I mean, being French, I'm not able to pronounce very well. He was studying the tide in the North Sea. So you see, this is England, France, and Norway. And this, this is the chart he produced in his paper about 2 centuries ago. But this is a nicer version of the chart. So these light blue lines are cotidal lines. These are lines where the tide is high at the same time or low at the same time. So for instance, for this, I don't know if you can see my mouse.
Yeah.
Yeah. So for this cotidal line, the tide is up, say, at noon. For this one, the tide is up at 1, at 2, 3, 4, 5, and so on. And for this one, the tide is up, say, at 6. But since the period of the tide is of 12 hours in this region, it means that along this line, at this point here, this yellow point, the tide is up at noon, while along this line it's down, it's low. So these yellow points where the cotidal lines meet have no tide at all, and you are call them amphidromic points. And I think the term amphidromic comes from amphi, it's around, and dromos is the velocity. Because if you draw, I don't know if you can see this red line here, is the velocity field associated to the tide. I mean, it's not the whole velocity in the sea, but the one associated to the tide. Of course, it's perpendicular to the cotidal line, which are, I mean, wave fronts, actually. And so the velocity of the tide that goes around these amphidromic points. And you see several vortices here, one here, one here. And even a saddle here, I will discuss that later. And actually, this is due to the fact that also for the tide, you can put, you can describe it by means of an order parameter, which has an amplitude, h, which is the height of the tide, and then a phase. So this chart also displays not only the wavefronts, but also the lines where the amplitude is constant. For instance, here along this dot lash line, the amplitude is of the order of 1 meter. And so you have these point vortices, and such point vortices exist all over the oceans. So this is a map from Wikipedia. You can see here several point vortices in the Pacific Ocean and also in the Atlantic, I mean, everywhere. And you see, so there are several, say, eigenfrequencies for the tide, several harmonics, if you want. And the most important one has a period of 12 hours and 25 minutes. And the white here, cotidal lines, are separated by 1 hour and 2 minutes, which is exactly 1/12. So, and indeed, if you make a round here, you will see that there are 12 lines gathering on a vortex. It means that if from the 12th you add another 1 hour and 2 minutes, you go back exactly on top of the first one. And indeed, it means if you make a round trip, the phase varies by exactly 2 pi. And so you have a quantized circulation. So the fact of observing point vortices is really due to the structure of the order parameter. And this, and I show here another result. It's for an open electromagnetic resonator. And I'll be brief, but you see also vortices and saddles. And these are experimental results of the group of Stockman a few years back. And people in the group of Bristol, Nye, Ashnal, and Hane, noticed that actually in this case, of course, as we saw, the vorticity is quantized, but you have another topological index, which is called the Poincaré index. So again, consider a 2D system where the order parameter has an amplitude and a phase, and the velocity is the gradient of the phase to a prefactor. So consider here a closed fixed contour, C, and draw on each point of this contour the velocity field or the gradient of the phase, okay? So we know that the circulation of the gradient of the phase is an integer times of 2 pi, and this is this IV, which is the vorticity, okay? But if you consider the polar angle here, theta, with respect to a given fixed direction, say the horizontal direction here, you see on my drawing here, theta increases, and so on and so forth, until it comes back to itself. So theta has made a round trip of 2 pi. And this variation of theta has also to be an integer times value, I mean, a multiple integer of 2 pi. Of course, I mean, you have to go back to the same. And theta is not the same as chi. For instance, it's very simply seen if you change v to minus v. Of course, this IV, this vorticity, will be changed into its opposite. Instead, if you change v to minus v, theta is changed to theta plus pi, which is a constant. And IP is not affected. So indeed, vorticity and Poincare index are not the same things. And as an example, I will consider, say, a vortex. So here I represent the integration contour, schematically in black, the streamlines, and in green, the wavefronts. And the vorticity can be anything, any integer, but the Poincare index is always +1. And I will try to convince you of that by this small drawing. Consider, for instance, a vortex where the velocity is negative, not in the positive direction, but in the negative, like this one, okay? And I will consider the orientation of the velocity when you go from 1 to 2 to 3 to 4 and so on and so forth, and make a round turn. And you see that this small vector makes a 2 pi turn in the positive direction. There is an increase from 1 to 2 and to 3 and so on. So the Poincare index is +1. There are other interesting points where the Poincare index is not 0. These are, for instance, saddles. A saddle is a point here where the velocity streamlines behave in this way. You have one contracting and one diverging region. Again, here in purple, the integration contour, and in green, the equiphase. So the saddle is not a vortex, the vorticity is 0, but the Poincare index is -1. And you can again show that. I'm just plotting here the velocity, the direction of the velocity. And you see when you make a turn in the positive direction, the velocity here changes in the negative direction, gets a -2 pi. So IP, the Poincare index, is -1. And the last type of points we will consider are nodes, which are, remember, the velocity is the gradient of the phase, and the node is a minimum or max of the phase. Here, for instance, it's minimum. So the streamlines in green are going away. The equiphase are, no, the streamlines are in black, sorry. The equiphase are in green, and again, the integration contour. And again, you can show that, of course, the vorticity IV is 0. This point is not a vortex. And the Poincare index is +1. Okay, so, I mean, this is something very simple, actually, but it changes the way one may, for instance, consider a simple phenomenon such as vortex, anti-vortex annihilation. One often has in mind that it suffices to take a vortex with vorticity +1, to bring another one with vorticity -1, and they may collide and annihilate. That would be okay for the vorticity, but not for the Poincare index, since they have both the same Poincare index plus 1. So you need to involve other critical points. And for instance, the people at Bristol suggested a mechanism they call the dance of the saddles. So you consider here two vortices of opposite vorticity embedded in a flow represented there, and let them get closer and closer. And so tell me if you see, I'm trying to make to show a movie there. Can you see the movie?
Yeah.
Good.
Well,
So here in the circles are vortices and the diamonds are saddles. So when the vortices get closer and closer, the saddles also get closer, but they don't annihilate. You see, they move apart to let the vortices get even closer, and eventually they all die exactly at the same time. Let me show it again. So saddles collide, move away, and eventually everybody dies at the same time. So this satisfies the conservation of the vorticity, of course, because this guy up there has vorticity, I don't know, +1 and the other one -1. But also of the Poincare index, because as I said, vortices have Poincare index +1 and saddles here -1. So the total Poincare is 0. So it's okay if they disappear together. And actually, this, maybe I will not spend much time on that. This was well known also to people who were studying quantum phase slips, but they were not by that time interested in saddles. We've worked with people in Nice, in southern France, who observed this phenomenon. So what they do, they shine a laser onto a nonlinear cell, and they image the output. Okay, so and this is one of their results. And as you can see, they observe clearly vortices and also a saddle. I mean, they are not the first to observe saddles or vortices, of course. And we also worked with people in Italy at Lecce. So they consider, as I said, polaritons, and you see they are able to create a large number of vortices. These are the red spots here. It's difficult to see, but with a plus or minus. And also saddles, I think, are here blue diamonds, and nodes, which are white diamonds. Yes, this rectangle here is an increase is a blow up of this region, and you see a negative vortex, 3 saddle, a repulsive node, and an attractive one. Maybe, yeah, I don't know if I will discuss the experiment of Nice. Maybe I'll have some time to discuss. So what they do in Nice, so they have only access to what they feed. I mean, what is the light they send, and to the output. So they know the output, but in between they cannot image what's in between. And for this system, the direction Z of the beam plays the role of an effective time. And what they observe that the output depends, of course, of the input. And for instance, they take an input which is here of that type. It's a cross-section of the intensity at the input. And depending on the different phase they put between the different parts of the beams they send, they observe these output. And we did some numerical simulations confirming that we have a code that indeed mimics where the output observed in the experiment. And there are no free parameters here. All the parameters of the nonlinear equation, which is a nonlinear Schrödinger equation, are given by the experiment. So since we are confident that we know how to describe the output, we are confident also that what's in between is accessible to the numerical simulations. And in these simulations, we often observed a mechanism of vortex formation, which is this one. You have two nodes here, a repulsive and an attractive one, which collide and create two vortices. And this conserves also, of course, the vorticity, because you see these two vortices, this guy is a negative vortex and this one a positive one. But also nodes, remember, they have Poincare index +1. So here the total Poincare index is +2, and it's the same here. And actually, this mechanism of vortex formation can be described by a Pavloff bifurcation, where you write the velocity field under this form. You have two parameters here, this sigma, which is constant and +1, and this mu varies. And when mu varies from positive to negative, the streamlines go from there to there. And you see that it looks like what you observe in numerics. But there is a caveat here by the fact that this velocity field is not a gradient, but you can modify it. I mean, it's not very difficult. You can define this object, which is a gradient of a phase. This V here is not the same as this one, but it's said to be orbitally equivalent in the sense that it has exactly the same straight lines. So you can observe this bifurcation with an object with a velocity field, which is a gradient of something. And on top of that, it verifies the quantization condition because simply it's the argument of complex. You can also observe the dance of the saddles proposed by the people from Bristol. You see here, this is a numerical result within the cell. And here it's a bifurcation also. Okay. And I will not comment on that. So you're happy. These elementary bifurcations are relevant to describe some experiments. And since they are described by indeed Pavloff bifurcation, I mean, one of the elementary bifurcations, you suspect or you hope that these mechanisms are universal. So let me focus more on the experiment led at Lecce for polariton systems. So it's a 2D system where the polaritons are created here at the center, and they are surrounded by a repulsive barrier. And the top A plot is it's a cut through a diameter. So they nucleate here the polaritons at the center, either at low energy here, the blue plot, or at high energy here, which is the green plot. And you see, it seems, I mean, more turbulent. And indeed, people at Lecce, experimentalists have led some, for instance, they can prove that they observe the Kolmogorov scaling, which is expected in a turbulent system. So you expect that this red here system is indeed turbulent, and it is. So at high energy wind. So what should I say? Yeah, so what I focus on this high energy data. So what they do, again, they shine light here, which create polaritons in the center. The system spreads, hits the boundary, and then becomes turbulent. And here they have access in real time to the intensity of the system and also to the velocity, because, yeah, I didn't say, but as in the previous experiment, here for the polaritons, it so happened that, remember, the system is created between two mirrors. It's a Fabry-Perot, so to say. And these mirrors are excellent. I mean, they have a reflectivity which is 99.95%, but it's not 1. It's not 100%. So there is some leakage. And this leakage gives you information on the intensity pattern and also on the phase pattern if you interfere with the reference beam. So that's why they got the phase, and they can measure by the grade of the phase the streamlines. And this is from this experiment. You see here in this two upper plot, they observe the collision of two nodes, one repulsive, one attractive, which creates two vortices. Or also the annihilation of two vortices and two saddles here. Okay, so up to now, I've presented, I mean, nice plots, and indeed these saddles and nodes are also relevant. But indeed, what's the use of seeing this nice structure? And I'll try to justify that these are important to describe some features of turbulent regime. So let's go. So again, this type of plot here is what is observed in the experiment. They are able, in the polariton experiment at Lecce, they are able to observe a lot of saddles, nodes, and vortices. And let's try to suggest or to propose mechanism for the creation of so many vortices and saddles and nodes. So we will consider the simplest possible mechanism. So the simplest one, actually, it's a saddle node bifurcation here. From nothing, you create a node and a saddle. And that conserves, of course, vorticity, because none of these objects carries vorticity, but that also conserves the Poincaré index, because node have Poincaré +1 and saddles -1. And also consider a slightly more involved mechanism where two nodes collide and create two vortices. I've discarded the mechanism where two saddles and two vortices collide because it's a four-object mechanism. It's much less often observed. So let's write this mechanism as chemical reactions and write reaction rates A, B, C, D, which are parameters of the model. And just consider, say, rate equations like in elementary chemistry. For instance, it's kind of a predator. For instance, consider what's happening for the saddles here. So they may be created from the scratch at a rate C. So if you call S of t the number of saddles, ds dt is C for this direction. From nothing, you create one node and one saddle. But also, one node and one saddle may collide and annihilate at a rate D. So this is this contribution here, minus D and S, N being the number of nodes, S number of saddles, and so on. You write 1, 2, 3, 4 equations, one for the nodes, one for the saddles, one for the vortex with vorticity plus, V plus, and one for the vortices with vorticity minus. Okay, and since actually you'll see in the experiment there are many vortices. To simplify the description, I consider that the upper chemical reaction here is unidirectional. You go from left to right, but not from right to left. So you take the parameter B as 0. Okay, So the equations simplifies. The equations simplify is B equals 0. And as a further simplification, you assume that the number of plus and minus vortex are the same and are equal to the total number of V divided by 2. And you can justify that by the fact that actually the difference V plus minus V naught, V minus, should be a constant if you don't import angular momentum to the system, and you don't. And then you rescale the quantities, and you end up with equations for rescaled, say, small v is capital V divided by a scaling factor n naught, and tau is t divided by a scaling factor t naught, and you end up with a system of 3 equations with a single parameter, gamma, which is connected to the reaction rates. And this gamma governs the qualitative features of the dynamics of the system. But of course, if you want a detailed comparison with the experiment, you need to know what is N naught, or to fit what is N naught and T naught. But really, the qualitative features are governed by a single parameter. So now you try to describe with this simplified and kind of phenomenological model, you try to describe the experiment. So again, for instance, here it's a plot of the experiment at t at 15 picoseconds. This is the intensity pattern, phase pattern, and from these 2 plots, you can compute where are the vortices, the nodes, and the saddles. You can count them and plot the number as a function of time. And this is what is done here in the upper plot. So the dots are experimental results. So in blue, it's the number of nodes as a function of time. In orange, the number of vortices, and in green, the number of saddles. And forget for the time being what is called here stage 2. Consider first up to time, which is here TC 56 picoseconds. So you see that you have an increase in saddles and nodes, in saddles and vortices, and not so much of nodes. And this can be described by the elementary kinetic equation I wrote. These are the continuous lines here. You can check also, I mean, this is not so important, this plot. It's the same information as above. It's V divided by S, the number of vortices divided by the number of saddles, and number of nodes divided by the number of saddles, just because the total Poincaré index, remember nodes and vortices have Poincaré +1, and saddles have Poincaré index -1. So the total IP Poincaré index is N plus V minus S. And if it's a constant close to 0, of course, V divided by S plus N divided by S is 1, and it is what is observed here. So you can indeed fit by the simple kinetic model the increase of the number of vortices and saddles. But something happens there after 56 picoseconds. Suddenly, the number of vortices and saddles decrease abruptly, whereas the number of nodes is not so much affected. And maybe I'm short on time, so I'll be fast, but you can show that actually after 56 picoseconds, these are experimental curves. What? Yeah. Okay. Where there is an echo. Okay, never mind. You plot the kinetic energy as a function of. I mean, you do a Fourier analysis of the kinetic energy, and you can show that the kinetic energy in some range scales as k to the power -5 5/3, which is the expected turbulence scaling. But this occurs only for times before this 56 picoseconds. After, if you average in a time window after this 56 picosecond, the scaling disappears. So this means that the turbulence is decaying. And so you can show that there is a tendency of end of clustering. The vortices which were clustering no longer do. I mean, it means these clusters decay, which allows clusters of opposite vorticity to meet and annihilate. And so since here you see that the nodes are not really important, you try to use this Bristol mechanism which was earlier discarded, where two vortices meet with two saddles and annihilate. So this gives you another parameter in the plot, and you don't change the other parameters, and you're able to describe this decrease. So I'm about to end. So this description is purely phenomenological. You may say even empirical. It has, for instance, it does not really explain why something happens at 56 picoseconds and why the change is so brutal. But it has some relevance to describe the experiments. So I'm about to conclude. So if there is a take-home message here, this is the fact that quantum vortices carry two topological indices, not only the vorticity, but also a Poincare index. And we identified in several experiments two mechanisms of vortex formation, which we feel topological and quantum constrained. And these mechanisms involve critical points which are different from vortices. And these concepts were well known to people studying singular optics. That was developed by Nye and Berry in the 70s. But we believe these are relevant for quantum fluids. And the effective kinetic description I just present, I mean, with all due respect, there's some similarities with the Landau mean field. It's a mean field. And you see in Landau mean field, you need to identify the proper order parameter. Here, you need to identify the proper dynamical variables, actually, which are the number of saddles, vortices, and nodes, not only vortices. Earlier kinetic description were not including nodes and saddles and were not so successful. I mean, in Landau mean field, you need to also to use the symmetries of the system when you expand the free energy. Here, what you need to use are the topological constraints. And as Landau mean field, you at the end, you use some empirical parameters. For Landau, these are the coefficients of the series expansion. Here, these are the rate equations. But of course, this is only a schematic description. And for instance, it would be very interesting to try to include spatial correlations between these critical points, which is absolutely not done in the approach I presented. I would like just to finish by presenting people which have been involved in this analysis. So there have been two collaborations. The first one in blue, both involved Thibaut Congy, which is now at Newcastle. And the experiments were done in the group of Robin Kaiser by his PhD students Pierre Azan. And the second experiment in Lecce were done in the group of Dario Ballarini with his PhD students Roberto Panico and experiment and theoretical support by Alessandra Lanotte and Giovanni Martone. Giorgio Ciliberto was doing his PhD with me. And with that, thank you for your attention.
Thank you very much for the talk. We still got time for a few questions if you are available.
Yeah, I am.
Okay. Questions from the audience. If someone on Zoom wants to ask a question, please speak up because I don't see the Zoom right now here. Yeah.
So I guess it was in the S over V and the nodes, those graphs where they showed the increasing and decreasing. Is there a reason why there's a gap in the data right in the middle?
Yeah, I don't know. There are some points missing and I have no idea why.
Okay.
But I hope they didn't hide some strange points by removing them. No, I think I have no idea.
Is there an extension of these ideas to 3D, or is this art specifically for 2D?
No. You can show also that in 3D the Poincare indices are there. This has been studied in detail by again Berry and Mark Dennis people, and also Isaac Freund was doing experiment on actually linear light. Observe this behavior also in 3D settings.
And in 3D, are there also just two topological indices, or are there more?
I think no, there are only two. It depends of the codimension of the lines you're observing. But say for the vortices, for instance, are lines, no longer points. And but again, you can define a Poincare index and of course a vorticity.
Mm-hmm. Good. Any further questions?
Quick question.
Oh, Michael, yes.
Do you have any insight into why the formation of these Onsager vortices is so dependent on the boundary conditions? I know Wegu did some studies, and if you have a sharp boundary, I guess you get the Onsager vortices, but if you have soft boundaries, then you don't.
No, I have no idea. But I guess even, I mean, on manifold without boundary, you should expect clustering. But no, no, I have no idea.
Okay.
But no.
All right. Any further questions? If not, let's thank Nick once more for a very nice talk. Thank you so much.
Thank you.